to think that a statistical model is not physically based. A statistical model is not deterministic. This is the only thing that you have to take into account. But a statistical model can be physically based. You can formulate the continuity equation, conservation of mass, conservation of energy, in an uncertain framework. This is extremely important because there is a widespread convincement in the literature, not to speak in the technicians and in the professionals, that statistical models are the counterpart of physically based models. This is not true. And it's extremely important because these people associate statistical modeling with the lack of knowledge. So they think that if you have a full knowledge of the process, then you use a deterministic model. If you don't have the full knowledge of the process, you use a statistical model. This is not true. This is not true. The truth is that if there is uncertainty, you use a statistical model. If there is no uncertainty, you use a deterministic one. But the statistical model can be physically based. It is extremely important to highlight this premise because otherwise you can't understand the benefit of a statistical model. The benefit is that it allows you to deal with uncertainty, to treat uncertainty. That's it. And you may say to me, what is the counterpart? The counterpart is that the model is more computational intensive. This is the problem. The deterministic model is not computational intensive usually because it's an analytical equation. The statistical equation usually is simple, but it takes time, computational time, to be developed. So this is, in my opinion, the problem in using statistical models. Not the fact that they are not physically based, not the fact that they indicate lack of knowledge. The problem is just the computational requirements. Okay. Now, given that I say that I'm referring to random events, of which I want to study the chance, let me define what is a random variable then. And because in statistics we use a random variable, deterministic variables are studied by deterministic models. In statistics, when you use a statistical model, you describe a random variable. So basically, the random variable is simply an association from a random event to a real or integer variable. Usually I say it's an association between a random event and a real variable because real variables may include integers as a special case. Basically, what I mean to say is that I see a flood, a river flow, I see an overflow. I can't study this event without associating the event to a variable. And therefore, so far we associated the event to the river discharge. Implicitly, we made this association. We associated the event to a real variable. Now, the random variable is just the same association, but there is the term random as an additional specification. So I associate a random event to a real variable. So I'm again studying the river discharge, but I am assuming that it's random. An essential concept, if I want to study a random event, its probability of occurrence is its probability of occurrence. So I need to define what probability means. Of course, we all know by intuition what probability means. When I say this is a probable event or this is an unlikely event, of course, it means that I already have an intuition of what probability means. Okay, so if I say the probability of a party to win the election is very high, I mean that the party probably will win the election, but still we need a formal definition if we want to use it. So, because when we use in a colloquial the term probability, we don't use it in a quantitative way. If I want to use probability in a quantitative way, by associating a number to probability, I need to define it usefully. So what is probability? Probability, let me start by saying that there is not a unique definition of probability, and probability must obey to 4 axioms, which are called the Kolmogorov axioms. So what are these axioms? First of all, 0, let me indicate the probability of an event to occur with P. Okay, P is probability. Okay, then 0 is probability is comprised between 0 and 1 included. So this is the first definition. When we speak of probability in quantitative terms, we have to associate to the considered event a number between 0 and 1. Perfect. So the probability of the impossible event is 0. And with this symbol here, I mean probability of the impossible event. And instead, the probability of the certain event, let me use the symbol C, is 1. And now, let me say the final one. If A and B are mutually independent events, if they are mutually independent events, the probability of A and B, this means unified, is equal to the probability of A plus the probability of B. Mutually independent means, first of all, that these are mutually independent outcomes from the same event. Sorry, it's not rigorous in my definition. Not mutually independent event, because 2 independent events may be a landslide and a river flow. No, these are mutually independent outcomes from the same event. So basically, let's think about tossing a coin. Tossing a coin, we have 2 possible outcomes. Head and tail, and the probability of head is 0.5, the probability of tail is 0.5, we know that. So you see that, first of all, the 4 axioms are respected, because the 2 probabilities that I assigned are comprised between 0 and 1, and I respected these 2 outcomes because, of course, these 2 events have a probability different from 0 and 1, but this is fine because these 2 outcomes, are not impossible and certain, and the probability of getting head or tail, so the probability of getting one among between these 2 events is given by probability of head plus probability of tail. So basically, probability of head is 0.5, probability of tail is 0.5. If I say what is the probability of getting either head or tail, is 1, of course. So this is the 4th axiom. Okay. Here the term unified means that you unify the 2 outcomes. So the probability of getting head unified with tail is indeed 1, because these are only the 2 possible outcomes. Still, these axioms don't tell us how to estimate the probability of head and the probability of tail. So if you don't know anything, if you didn't know anything about this experiment, head or tail, how could you estimate these probabilities? Or you may have an odd coin. a loaded coin, sorry. A loaded coin means that you have a higher probability of getting one of the two outcomes with respect to the other, and you may not know it. So these axioms don't tell you how to estimate individual probability. And if I ask you how would you estimate it, what would you say? You would say, I may try. I try to toss the coin 100 times, and then I understand what is the probability. This would be correct. But still we don't know how to estimate these probabilities. We have the intuition that we may try with experiments, but this is just an intuition. Now, these 4 axioms don't provide a definition, because as I said, if you provide a definition, then you also have the means to estimate the probability. These axioms are just necessary conditions that are dictated to your definition of probability. We still don't know how to define it. So let me now define probability. And this gives me a way to compute it. The literature proposes 2 main definitions of probability. One definition is the frequentist definition. And I will click on this. Let's suppose that you select an experiment and you perform n times this experiment. So you perform an experiment n times. Then you define the probability of a given outcome A as the limit for n tending to infinity of NA divided by n. So the number of outcomes equal to A divided by the number of total number of experiments. This is what you would do by tossing a coin. Okay, you perform 100 trials, and then you see how many times you got the tail. Probably it will be like 55, and then you get an estimated probability by dividing 55 by 100. Perfect. This is quite, and this definition meets all these axioms. Try, and you will see that this definition is fine because it meets the axioms. And this is the definition on which we will stick. It's very easy to understand. I just would like to say, to anticipate, that a major problem here is the fact that if the number of outcomes is finite, is limited, then no problem with this definition. If you have infinite outcomes, like with a real random variable, this definition doesn't work, so we will need to adapt it. But for now, let's suppose that you have a finite number of outcomes, and then you can use this definition. Perfect. Let me see if the progress of the slides okay, I would say that it's fine so far. Yes. Now, let me just say that there is another definition that is very popular, which is the Bayesian definition. The Bayesian definition of probability, it's more general than the frequentist definition, because the frequentist definition implies that you can perform an experiment. This is fine in water resources management because we get the data, and the data are basically the results of previous experiments, so it's fine for us. But let's suppose that you want to estimate in a rigorous way the probability of a party of winning the next elections. And you cannot perform experiments. You cannot make the election 100 times and see the outcomes. So this is something that, an example, an event where you cannot use this definition. Basically, what could you do? You could use the exit polls, or you could use interviews to people. Before the elections, you may interview people, but this is not the same experiment. Because these people, when they are interviewed, they are not in the secret of the voting room, or how to say in English. I think you understand me. And so when they are interviewed, they may say express a different vote, different participation of vote. So these are not really rigorous experiments. Basically, with these experiments, you gain an idea, you gain a knowledge on the event that allows you to make a guess, but it's not really a realistic experiment. So you get information that allows you to elaborate a guess. And when you elaborate this guess, you of course have to respect these axioms. So you cannot say that if there are two parties, that one party has a probability of 0.8 and the other party has a probability of 0.5, because the sum makes 1.3, which is not consistent. So basically, you elaborate a perceptual probability by using prior knowledge, and you make sure that this perceptual probability meets Kolmogorov's axioms. And this is what is called Bayesian estimation of probability. You use a prior knowledge to elaborate a perceptual estimate, and then if there is the possibility to perform experiments, then you update your prior knowledge. I'm not interested in, as I said, in discussing much further Bayesian probability. I just wanted to let you know that probability can also be expressed in a perceptual way, which can be rigorous. If you use all the information that you have available, it's the only way of expressing a probability, maybe the only way to express a probability, and it is rigorous. And if the estimation is carried out rigorously, with both definitions, you get the same estimate of probability. Like, think of tossing a coin. You easily predict by using your prior knowledge that the probability of getting a tail is 0.5. This is a Bayesian estimate. And then if you perform the experiment 100 times, you get a frequentist estimate. And in this case, you will likely converge to the same outcome. Okay. So, now we have this frequentist definition of probability. Now let me explain what happens when you deal with a real variable. And basically this estimate allows you to get a guess of the probability by counting, as I said, the number of times that you get a given outcome. But if you deal with a real variable is includes an infinite number of digits. So if you perform an experiment with a real variable, like observing a river flow, and you count the number of times that you observe, like 10, 1, 2, 3, 4, 5, 6, probably the number of times that you observe this value is 0. Because of course, when you have an experiment whose outcomes are several and several and several, tending to infinity, the probability of getting each one of them is 0, according to this definition. You may perform 1,000 experiments, and you will get 0 times this value. But this doesn't mean that the probability of getting this value is 0. It's tending to 0, but it's not 0. So how can I define probability in this way? I need to elaborate an additional concept. So let me draw a straight line, the line of the real numbers. So let me draw the line of the real numbers. Starting from, okay, let me start from nothing. It's minus infinity plus infinity. Or let's refer to river flows. River flows is from 0, because it's a positive value, positive variable, to infinity. And let's suppose that here you have a variable q star, a given value. Its probability is 0, according to the frequentist definition. But we understand that it's not 0. It's tending to 0, but not 0. So what is a possible way to solve the problem of getting an estimate of the probability of q star? Okay, the problem could be, the way forward could be that you take an interval delta q around q star. And you count the number of times that the observed river flow falls into this interval. And of course, the number of times that falls inside here depends on the size of delta q. If delta q is large, you get a huge number of numbers falling into it. If delta q is very small, the number decreases. And so, of course, we cannot accept such a definition, because we cannot say that the probability of getting q star is equal to n, and that's it, because n depends on delta q. So we cannot accept such a definition. We need to elaborate a different definition. And but let's say that given the fact that n decreases for decreasing delta q and increases for increasing delta q, we may think of computing the quantity n divided delta q, which, I mean, is something that is independent from delta q. And we may call it, by using the symbol lowercase p of q star. But let me also write here, let me rewrite it, because otherwise, because I need to compute this estimate for delta q tending to 0, because I want to focus on q star. I want to stay close around q star. Okay? So let me say that the rigorous definition is lowercase p of q star is equal to the limit for delta q tending to 0 of n divided delta q, where I'm not really very rigorous in providing this definition, because I have dependence on q star here, and I don't have any dependence on q star on the right-hand side. So let me just put here this symbol in order to highlight that delta q is centered around q star. Okay? Now, what I got there, what I got with this definition is something different from the previous quantity that referred to discrete variables. In fact, I use a different symbol. So basically, they are different, and you can see that they are different, at least because if you look at the dimensions, here I have a number, dimensionless number, but at the denominator I have a quantity that has a dimension. So there is a difference. They are not the same quantity. And if I define this one as probability, I may define this second one as probability density. Because indeed, this one is a density. And what is the parallel between these two? Are they consistent? What is the relationship? And in order to explain the relationship between them, in order to show you that these two definitions are very consistent and related, I want to discuss with you what happens if you integrate the probability density between two given values of river flow. So let me compute below here the integral between Q1 and Q2 of P Q star in the Q. Or let me say I have to drop the star now, because Q star is an assigned value. In this case, I have to drop the star because Q is varying between Q1 and Q2. So what is this number? And let me show here the two numbers Q1 and Q2. What is this number? What is the integral of the probability density between Q1 and Q2? It gives back to me the number of times that Q falls into the interval Q1, Q2. And let me call it N Q1 minus equal than Q minus equal than Q2, sorry, not minus, minor equal than Q, minor equal than Q2. This is what I find here is N Q1 minus equal than Q minor equal than Q2. So basically this is basically this is let me think, because in order to establish the connection, yeah. I found that there is an inconsistency in the notation, because basically in this definition here, I try to speak slowly in order to, I want you to understand, there is an inconsistency in the notation that we need to resolve. Basically here I indicate with that the total number of outcomes, and here I use the same symbol to define the density, which is not correct. So this is the number of times that I fall with the observation in the interval delta Q. So I think that I should write here number of delta Q, okay, delta Q, and the denominator instead I should add the total number of outcomes, which I forgot. I realized, and then I think that everything else is fine. Everything else is fine, but I have to put n here. Because, you know, I forgot to divide by the total number of data. This is important. And also I realized that the numerator, again, I use the same symbol for the total number as for the number of times that I fall in the given interval. So I need to update the notation. And then I can say that the integral then is equal to the number of times that I fall between Q1 and Q2 divided by n, and this is equal to the probability, so I get back to this definition of Q1 minor equal to Q minor equal to Q. So let me describe what I did so far. Basically, I started from the definition of probability for a discrete variable. And then I think this is quite straightforward. And then I passed to the random real variable. And for the real variable, I said I needed to adapt it. So still, I can count the ratio between the number of outcomes that meet the given number and the total number, but I have to divide this number, I have to refer this number to a finite interval delta q, and I have to divide this estimate for delta q itself to make it independent from delta q. And then if I take delta q tending to 0, I get an estimate of something that I call probability density. At this stage, you may not see the relationship between the probability density and the probability that I computed before. And then I said, let's look at what happens if I integrate the probability density. If I integrate the probability density, then I refer to a finite interval, not anymore to a given number of river flow, but I refer to a finite interval of river flows. And then if I compute the integral, I get back the probability of the river flow falling into that interval. And let me say, by using the intervals, basically, I transformed the real variable in a discrete sequence of intervals, and therefore, it's straightforward that I should get back, is what I am expecting, that I should get back to the definition that I gave before for the discrete variables. So basically, the probability density is the derivative of the probability for a real variable. So for a real variable, I can define both probability and probability density. One is the derivative integral of the other. It's important to note that for a real variable, probability and probability density contain the same amount of information. They are the integral, again, and the derivative of the other. Okay. So let me summarize. One important quantity when we speak of probability of river flows probability of not exceedance. What is the probability of not exceedance? Sorry, I forgot the EA here. It is important for us because it's the probability of not to exceed a given river flow. And let's suppose that this river flow is Q star. So what is the probability of not exceedance of Q star? This is equal to the probability that 0 minor equal than Q minor equal than Q star and let me use a different Pn. I use Pn for probability of not exceedance, okay? And this is simply the integral between 0 and Q star of lowercase q in the Q. According to the previous definition, basically I compute the integral now not between Q1 and Q2, but between 0 and Q. That's it. I call it Pn, it's the probability of not exceedance, and it's the integral between 0 and Q star of the probability density of Q in the Q. This is an extremely important indication for us because it gives basically, if I know the probability of not exceedance of the river flow for a series of river flow values, I get an important